Did we show our homework yet?
Not yet. Hold on.
Okay, okay, just making sure. I don't want to miss that.
Okay. Time is it 1:01? Yeah. Okay, so I did say that I wanted to have people show their work to their camera. But before I do that, I just wanted everyone to know I've had some technical problems with my computer, and all the notes that I've been taking in class, everything, I basically have lost all that. So I think our most recent class, I don't know if I uploaded it to Canvas, the copy of the notes, but if I didn't, they're gone. All right. So, but everything seems to be okay now. Hopefully the class will work out all right today. We are going to finish up chain rule today. We're going to start implicit differentiation, and then we'll move on. All right. I would like to entertain any questions that you may have.
Hey, Professor, I do have a quick question. So while I was doing a homework, I'm not sure what's the problem number exactly, but I do have a statement. So I just have a lot of confusion. So I just came up with it was y equals under root sine x.
What was it? Y equals what?
Under root sine x inside.
Which problem was, or you just made up your own problem?
No, it was a problem there.
Oh, the square root of sine x?
Yeah.
You mean number 5?
Yeah, I think it's number 5.
Yeah, square root sine x. Yeah.
That one?
So, yes, sir. I mean, I was watching a video with it when I just finished it up. So your answer was 1/2 in bracket and then sine x, right?
Yes.
So, but I come up with a when it's bracket and there was a power negative 1/2, but in your answer there was no power of negative 1/2.
Okay.
So
Yeah.
Like, where did I make a mistake?
You didn't. So here's the thing. All right. When it comes to the square root of x,
right?
Okay, if you want to take its derivative, one thing you could do is, well, you change it to 1/2 power. And then when you take the derivative, the 1/2 comes down, and then you have x to the negative 1/2. You agree with that?
Yes.
Okay, now, if I clean this up, this is the same as 1/2, and then because this is a negative exponent, I can drop the x to negative 1/2 down as a positive 1/2. Do you agree with that?
Yes, sir.
And isn't x to the 1/2 the same as the square root of x?
Oh, okay. Okay, I see now why I was just like, what is going on here?
Okay, so I'm glad you brought this up because I want to say something about this. Anytime you see me take the derivative of the square root of something, I do not do this, okay? I go automatically to this. So the way I guess I remember it is anytime I take the derivative of the square root of something, my answer will always be 1/2 times the square root of that something. I don't even think about the powers being, I've like memorized this as a formula. All right.
Got it. Thank you.
So to do this problem, the outer function is the square root and the inner function is the sine. So to take the derivative, the way I would do it is I would say, okay, I have to do the blue first. So what is the derivative of the square root of something? So in my mind, I go, oh, well, I know that that's 1/2 and then square root of whatever was in here, which is sine x. Okay. Do you see that that's this formula right here, but instead of x, I put whatever was in here?
Thank you.
Then chain rule says now I can go in here and do the inner function, and the derivative of sine of x is cosine of x. And I guess you could leave it like that, or you just pop the cosine up top. Make sense?
Yes, sir, it does. Thank you.
Okay. Now on a test, if you were to write this, you would get full credit. It is correct, all right?
Okay, cool. Thank
It
you.
just looks different than mine, that's all. Other questions?
I was going to say if you could go over number 19.
19?
Yes.
Okay, yeah, 19 is a little messy. Well, you know what? I helped somebody out with this earlier today. Maybe I can just show you the work. All right, so for number 19, you have h of t is t plus 1 to the 2/3 times 2t squared minus 1 to the 3rd. So what you first have to recognize is that you have a product between two things. And since you have a product between two things, you're going to treat the entire first factor as f and the second factor as g. And that means to take the derivative of h, you have to do the product rule. Does that make sense? Okay. Now, to figure out the product rule, I went ahead and wrote down over here what f was. Okay, f was this piece, so there's f, and g was this piece here. And then I just went ahead and figured out what the derivatives of those were separately. And then I'll just plug all the answers back in here. So when I take derivative of f, we have, again, an outer function and then an inner function. So you start with the outer function, which is something raised to the 2/3. And so we use the power rule. The 2/3 comes out in front, and then you rewrite that yellow here, you don't take its derivative, and then you subtract 1 from the power. 2/3 minus 1 is negative 1/3. All right with that? Then you have to say times, and now you have to take derivative of what's in here, the yellow. But the derivative of t plus 1 is just 1. Because the derivative of t is 1, and the derivative of 1 is 0. So you just get a 1 here, but you don't really need to write it because anything times 1 is itself. So I didn't include that. And then when you go for g, g is the same thing. You have an outer function, which is the cubed, and then you have an inner function, which is this. So you start with the cubed, take derivative, 3 comes out, everything in here, no derivative, squared. And then again, you have to go in and take derivative of what's in here. And this time you have to do power rule here. So 2 comes down, you get 4t, and then minus derivative of 1, which is 0. So I don't put anything there. And then I put the 4t out front with the 3 and make it a 12t. That make sense? All right. And then the next step is just plug everything in. Right? So f prime, I just take that and I just put it here. And then g, which is the original g here, plus, and now g prime, which was this answer. And then times f, which is the original function here. And that's it. What's circled here is what I'd want to see on a test or something. Don't worry too much about the simplification of it right now. We're gonna have to spend some time figuring out how to simplify these, but I don't want that to be the hang up for you right now. Does that answer the question?
Yes.
Okay. Anything else?
I had a quick question. For number 7, the final answer was simplified, but I know you just said that we're not supposed to worry about that, but so whatever we get from following the formula is the final answer, right?
That'd be okay. Yep.
Okay,
What I
good.
said to you all is that eventually what we're going to be doing is setting our answer equal to 0, which means we're going to have to somehow solve a very nasty looking equation, which is going to require algebraic simplification. But I just don't want us getting hung up on that at this point. Okay, anything else that you want me to go over?
Yeah, real quick. 46. So I just had a question. I mean, I solved it and all that another way, but I wanted to know if I could have flipped the square root of x plus 1 to the top. So it's 4x over square root of x plus 1. And I
Yeah,
didn't know if I could have done that.
let's do it both ways. This is kind of where I wanted to start class, with a problem kind of like this. So this
Okay.
is a good place to start with.
Yes.
So here we have to see, we're trying to find the derivative. We're actually, it's asking us for this first and second derivatives. So we have to take the derivative, get an answer, and then take the derivative again. So when we do this first derivative, we need to recognize that we have a big division here. And so we have like an F over a G. And so to do a derivative of a quotient, we have to do the quotient rule. All right, so since I know I need quotient rule, what I'm going to do is over here on the side, I'm going to write down what F is. F is just 4x. I'm going to write down what G is. G is the square root of x plus 1. And now I'm just going to find their derivatives, and then I'll just plug everything in and get an answer. So what is the derivative of F?
4.
4, okay, that's the easy one, right? Now the derivative of G. Think about how I started class today. If we take the derivative of the square root of something, it's going to be 1 over
2
2 square roots of that something, right?
Right.
And then chain rule, because that was the outer function was the square root. Now you have to go in and take the derivative of the inside. What's the derivative of the inside?
The inside would be just 1, right?
1, right? Because derivative of x is 1, derivative of 1 is 0. Any questions on that from anyone?
So the chain rule only applies to this, I guess not only to square root, but if it's something inside.
That's right. Yeah. So one of the big challenges as a Cal 1 student is recognizing what's happening within a function. Is it multiplication? Is it division? Is it composition? Composition is when you have a something inside of something. That's what we have here. We have composition, where here we just have a term, you know, we just use our basic derivative here. So that's the part of the challenge, is trying to differentiate, well, I shouldn't use that word, is trying to distinguish the operations from one another. All right, so let's continue. Now I'm ready to find this derivative. So the derivative of this should be this formula, just plugging all these little pieces in. So f prime was 4 times g, which is the square root of x plus 1, minus g prime, which was 1 over 2 square root of x plus 1, times f, which was 4x, then the whole thing divided by, and this is about the only part of the problem that's nice, which is g squared, which is this thing squared. And when you square a square root, the square root goes away. So you just get x plus 1. Any questions on this?
Nope.
Okay. This is where things are going to suck, because we're supposed to take the derivative of this now. And this is a mess. So I am forced in this problem to clean it up algebraically. So just see if you can follow me through this work. Right now, I'm just cleaning it up. All I'm going to do is move this 4x on top here and realize that that 4 and that 2 reduce out. So I will get a minus, that's this minus sign. I get a 2x on top. And on the bottom, I have that square root that was down there. And then all of that is over x plus 1. Any questions on that step?
I have a quick question. So for, I guess the one above it, there we don't put the square root, right? Because it cancels out. Like for g, how it's supposed to be like g squared.
Oh yeah, we could have done the square root. That's g, right?
Yeah.
And then we're supposed to square it. And that's why I didn't write it, because it kills off the square root.
Oh, okay, just make sure.
Yeah. I'll leave it there this time, and then on the next step, it's gone. Okay.
All right, thank you.
All right. No, good, good. All right. So I'm still not wanting to take the derivative of this, because this is still a big mess. I've got a complex fraction here. So what we're going to do is kind of what we did when we were doing limits. I'm going to try and put these together, right? Try and put them together. And to do that, I have to realize that this is over 1 and get a common denominator. So what would my common denominator be?
It's going to be the square root of
X plus
x plus
1.
1.
The square root of x plus 1. So I have to multiply square root of x plus 1 here on the bottom of this fraction and on the top.
And then the top would cancel each other out, right? The square root and the square root of x plus 1, it would turn it into something else.
Yeah, when those two hit each other, you basically have square root of x plus 1 times itself squared. So the square root goes away, right? But you still have the 4 in front. So you'll have the 4 and you'll have x plus 1. That is this right here. Right?
Yeah.
Then you have, let's say, the minus sign, okay? Then you have the other one's numerator, which is 2x. And all of that should be over their common denominator, right? Because they were both on top of this. So now we have square root of x plus 1 here. But don't forget, all of that is on top of x plus 1. All right, I'm going to go ahead. I'm going to distribute this 4 through here and here. So that really gives me 4x plus 4. And so I have 4x plus 4 minus 2x. Shouldn't that be 2x plus 4 then? Isn't that what that is? Oh, sorry. Yeah, is that right? 4x plus 4, then minus 2x. So we should get 2x plus 4.
Yeah.
Okay. Over the common denominator, square root of x plus 1. All of that still over x plus 1. It looks better, doesn't it? I mean, it definitely looks better than it did up here, but it's still pretty bad. I mean, you got a fraction on top of a fraction, right? So I'm going to do something else. I'm going to remember that if I have a fraction on top of a fraction, I can look at the bottom fraction as x plus 1 over 1. And now I can do the whole thing where you flip it. So this is where I bring this up as a 1 over x plus 1 and get rid of it down here. So here's where we are. We have 2x plus 4 on top. On the bottom, we have, now I'm going to do something strange here. All you're going to do is just agree or disagree with me that that's legal, right? 2x plus 4 on top. Instead of writing x plus 1 square root, I rewrote it as x plus 1 to the half. And then here I have x plus 1, and that's just, you know, x plus 1, right?
Yes, it is legal. And then you can go ahead and add the exponents.
That's right. Since these are both something to a power, same thing to a power, and they're being multiplied, we can add the powers. So I can take a half and add 1. And when I take half and add 1, I get 3 halves. So I have this. Now would be a good time to ask a question if you're not following that step. This is about as clean as it's going to be. That's y prime. That's our derivative. Our first derivative, right? We're supposed to find the second.
Oh yeah, it's going to get ugly in here.
Yeah, so y'all ready for the second derivative now? It's the same story we just had. We have like a top function f and a bottom function g, right? We have to do the quotient rule again. So to get our second derivative, we know it's going to be f prime times g minus g prime times f all over g squared. Where f for us this time is 2x plus 4. And g for us this time is the denominator, which is x plus 1 to the 3 halves. And don't miss the bus here, okay? If you have a question, this is the time to ask.
Oh, you're still going to show me
The other way. Yes, I will show you the other way.
I just wanted to be sure.
Yeah. Okay, so ready? Now I need to figure out what f prime and g prime are. F prime, that's the easy one. That's just 2. What about g prime? Let me call on somebody here. How about Axel? Is Axel here? I don't think I've seen Axel in a while. Let me see who have not. Daniela? How do you feel about giving me the derivative of this? Uh-oh, shit, okay. Okay, I just freaked out. Go ahead. How do you feel about the derivative of this?
It will be 3/2. And then just 1.
So remember, when you're bringing the power down, right? And then it's going to be subtract 1 from the power, which would be a half, right? But what goes in here? Are you going to take the derivative of this now, or are you going to wait and do it on the next part of the chain? Outer function, inner function, right? Start with the 3 halves coming out. Leave this alone. Then you go times the derivative of what's in here, which would be your 1. Right, Daniela?
Yeah.
Okay. I know we've done this, and we were doing this a little while ago, so I know you can do this. Just remember, when you're doing chain rule, take your time through the steps. That's the most common thing I see as a mistake, is people will try and do too much too soon, too much too fast. So they'll bring the 3 halves down, and then in here they'll put 1, because they went ahead and took the derivative of this. But you have to wait till the next step in the chain rule. Okay, so there they are. Now we can plug them in. So f prime, that we're doing this, that's 2 times g. G is x plus 1 to the 3 halves, minus g prime, which we just said is 3 halves x plus 1 to the 1/2. That was this. And then times f, so in parentheses 2x plus 4. And then the whole thing divided by g, which is x plus 1 to the 3 halves, but all of that squared. Now, I'm not going to simplify that, okay? I'm just going to leave it like that. Good thing they're not asking for the third derivative, right?
Oh my God. No.
Yeah, because then third derivative, we'd have to put all that together. But
Oh,
I think that's sufficiently enough work for now.
How far will we go with the derivatives? Like, how far down the rabbit hole?
We will be focusing most of our attention on the first and second derivatives, because they actually tell us something about graphs. The first derivative tells us the slope of the tangent line, and the second derivative tells us something about what's called the concavity, which tells us whether or not our graph looks like a frown or like a smile. The third derivative doesn't really have a geometric representation, so we stop usually at the second one.
But
Thank
in
you.
the homework, there is a problem that is to the fit that asks you for the 50th
Yeah,
derivative,
we're gonna do that.
which that one's fun.
Yeah, that we are gonna do that. I wanted everyone to see that one. Okay, so now what I'm gonna take this. Let's do this. Danielle had a question. This is what Danielle asked about in the very beginning, right? And I said, okay, I'll do this problem. And what Danielle said is, could you do it this way? So could you have written it like this? Okay, we all agree that that's the same original function, right? And Danielle said, could we bring that x plus 1 to the half, could we bring it up as x plus 1 to the negative half, right? That's what you were saying, Danielle?
Yeah, to kind of turn it somewhat into a fraction, I guess, right?
Yeah, and then do the derivative on this. And my answer to her was yes. If you do that, though, you now have to see you've created a product. And so you would have to use the product rule instead of the quotient rule. And so you call this f and this g, and then you do your product rule. So I'm going to do it because I said I would. So y prime should be, remember the formula for the product rule, f prime g plus g prime f. That's your product rule. So Danielle, since you asked, what's f prime?
F prime was going to be 4.
4, and then times the formula says g, so don't touch g.
Right.
Negative 1/2 here.
Uh-huh.
Plus, now you need g prime. So Danielle, what's the derivative of this?
It would be negative 1/2 x plus 1 to the, what is it negative 3/2?
Negative 3/2, yeah. So Danielle said, I'm gonna do chain rule on this. The negative 1/2 comes out first, then all of this, subtract 1 from that, you get negative 3/2. And then Danielle had to take the derivative of the inside of this, which is just 1. I'll put it here because why not? And are we done, Danielle?
No, we have to finish that off and multiply by the original f function.
Yep. So don't forget, we're doing a product rule. So we still need the f here, and that's 4x.
Mhm.
Okay, so let's write this down. This is y prime equals 4x plus 1 to the negative 1/2. And then here I can put that 4x and that half together, negative half, and that should give me a negative 2x. And then I still have the x plus 1 to the negative 3/2. That is a correct answer. Okay, that is the first derivative. Remember what our first derivative looked like on the previous one? This was our first derivative, right, over here. And then we started cleaning it up and cleaning it up and cleaning it up, and we got it finally down to here. This was our first derivative. This right here was what we got doing it the other way. And I'm telling you that that answer that you see right here is the same as this answer you see right here. Even though they don't even look like they're the same. Algebraically, they are. The thing I like about this, though, is we can do the derivative again now without having to worry a lot. So if we do the derivative again to try and get the second derivative, let's see if you can follow me on this. First thing I'm going to do is I'm going to take derivative of this. So the 4 out here, I'm just going to ignore. And now I have chain rule on this, right? We have something to a power. So the power is going to come out. So I bring the 4 for the ride. Power comes out, negative 1/2, x plus 1. And now I have to subtract 1 from this. So negative 3/2. Then I take derivative of what's in here, which is just 1. I don't need to write that, but I'm just, again, trying to be clear that I'm doing chain rule on that. Does everyone see that? That's derivative of this. Now I need to take derivative of this. And I have a minus sign there. So I'm going to put minus. Now here's where things get weird. This is a product. Do y'all see we have 2x times this multiplication? This had an x. This one, see, this 4 didn't have an x. That's why I just brought the 4 for the ride. But because there's an x here, I must do a product rule between these. And so now we have an f here and a g. So this minus sign that I have here, I'm going to put a big bracket here. And now I'm going to do my product rule on everything you see here in yellow. Ready for product rule? Here it comes. The product rule says I need to take derivative of f first, which f is 2x, so derivative of that's 2, times g, plus now the derivative of g, which is a chain rule, so I can bring the negative 3/2 out front, x plus 1. Now I have to subtract 1 from that again, so negative 5/2. Then take the derivative of what's inside of it, which is 1. And then finish off the product rule by hitting it with f, which is 2x. And that is the derivative, second derivative, I should say.
I have a question.
Yes.
Why did you add the negative 1/2 with the 4x?
Right here.
No, like all the way. Yeah.
Why did I put those two together?
Yeah.
Well, okay, so the one we don't need, right? That one, forget about it.
Mm-hmm.
I'm just trying to clean it up. So I just did, what's negative 1/2 times 4x? And half of 4 is 2, right? So that just becomes negative 2x. I'm just trying to clean it up. That's all.
Okay.
Right? It's all multiplication here. So because we have multiplication, we can kind of move things around. If it were addition or subtraction, we couldn't.
Okay, got it.
I had a quick question. So because we have two like terms in the sense of x plus 1 and then another x plus 1, could we do anything with that?
Yeah, we could start factoring, and yeah, there's a lot of things we could do.
Okay, I'm just making sure because I see it and that's what I'm thinking. I'm like, okay, I have these two things. I'm gonna pull that out and I'll put this over here and blah, 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 blah. That's okay, right?
Yeah. So I'll tell you all a quick story. I don't know, I'll try and keep it under 3 minutes. So when I was in graduate school, I I had to teach, I wasn't teaching Cal 1, but at big universities, when you take Cal 1, you go to lecture, and then once a week, you go to a thing called recitation, which is where you go into a room and there's somebody standing up there and you can ask that person questions about your homework, things like that, right? So when I was in graduate school, I did some of the recitations. So I would go into a class and there would be like 100 calculus students in there, and they would just start asking me questions about their homework, right? So I had this one student who had me work through a problem, and I got to the answer, right? And then I said, okay, we're done. We have the derivative or whatever. And then that was it. And like a week later, he came into the tutoring lab where I worked, and he just like barged through the door, and I was in the middle of helping a student, and he came up to me and he was like, you know, you made a mistake, you know, you messed up and you need to apologize to everybody. And I'm going to let the professor know that, you know, they don't have somebody who's competent in here. And the thing was, he was older than me. I was like 20 when I was doing that, and he was like 26. And so I think he just didn't like me because I was younger than him or something. So he started like getting mad at me. And anyways, it was a problem like this. It was a problem like where I had gotten an answer that, I don't know, maybe my answer looked like this, and I had stopped and said, okay, we've got the derivative, we move on. And the answer in the back of the book was that. And so basically all he was complaining about was the fact that he didn't know how to do algebra, right? And so I had to sit there and say, sit down, let's go through the problem. And I had to show them, you know, I told him, I was mad. So I was like, sit down, I'm going to give you an algebra lesson. And so I took him through all the algebra and got him to the answer, and he just kind of tucked his tail and left. But the moral of the story is this: in algebra, I mean, in calculus, the algebra is really messy. And I've told you this from the beginning, and I've tried to conveniently avoid it as long as we can. We're starting to get to the point where our derivatives are going to be ugly, and we're going to have to start cleaning these things up. All right, we're not quite there yet, but the algebra that's going to be involved to clean this up and make it look nice is going to take some work. And so depending on your level of algebra skills, this is where you might start to feel some weaknesses coming up. All right. And that's on top of having to learn all the rules, which is what makes things hard. So this is the second derivative we got, right? This was the second derivative we got when we did it this way. And what I'm telling you is that that answer is the same as that answer. They're exactly the same. You just have to, you would have to show they are. So you have to do a bunch of algebra to show they're the same thing. All right. Okay, let's move on. Yes. How about we do this? I said that I wanted to do it where you would at least just like show your camera, like that you tried to do some of these chain rule problems. So since we're recording this, I'm just going to give everyone a minute or two to just show me what they want, and I'll be back. It's recording you. So if you didn't do it, it's okay. But you know, I'm going to take this as a participation / bonus / like, if you're failing at the end of the semester and you didn't show me your chain rule work, then I'll say, why didn't you show me your chain rule work? Okay, that should be good.
You're gonna be able to take questions after class, right?
What's that?
Are you gonna be able to take questions after class?
Today I've got to kind of be out of here right at the end of class. I'm not going to have time.
Yeah, that's fine.
I apologize. I've got a commitment that I've got to get to before I get somewhere else, so I don't think I'll have time.
No, you're good.
But text me later or something. I'm going to be very, very busy. Just so y'all know, the next day, the next 5 days, I'm going to be super busy because I'm giving midterms to my internet students. So grading is all I'm going to be doing for the next few days. All right. So how about this? Let's say that y is equal to sine of 4x. I want us to, part A, I want us to find y triple prime. For part B, I want us to find y with a little parenthesis 6. And then C, I want us to find y with a parenthesis 40. Okay, so what does y with these three things mean here? Three little dashes.
Find a derivative to the third derivative.
Third derivative. So I need you to take the derivative 3 times. What does a little 6 up here in parentheses mean?
Same thing.
Same thing 6 times. And then what does this mean?
40.
40 times. Okay, so let's start with part A. So for part A, all right, y, let's do y prime. So y prime, please pay attention. We have an outer function and we have an inner function, don't we? This is composition, so we have to do chain rule. So let's see here. Is Gene here? Oh, Gene, you know what I called you last time. How about this? Gage, are you here? No Gage?
Yes.
Oh, Gage, you are here.
Yes.
All right, so what do you think about the first derivative? What do you got?
Will be cosine.
Cosine of what? What goes in here?
4x.
Okay, are you done?
No, and then the outside it'd be just 4.
Times 4. Okay, good. So I'm going to put the 4 in front. Is that all right with you?
Yes.
Okay, good. Everyone follow that? That's derivative of sine of something, which is cosine of it. And then you have to take derivative of the inside, which is just 4. And then we pop the 4 out. Perfect. All right, Gage, you want to keep going?
Yeah, I can
Second
keep going.
derivative.
Second will be,
So since this 4, Gage, since the 4 is attached to the front, right? A constant, remember that if you have a constant in front of a function, it just comes for the ride. Okay. So just bring your 4 down and now just focus your attention on this. So be thinking inner and outer again.
so then negative sign.
Negative sign of what?
4x.
Okay, and then are you done?
No.
Then what?
And the outside again will be times 4.
Times 4 again, right?
Yes.
Everyone see that? Okay, so now we have out front negative 16. Do y'all see where the negative's coming from? Because it was negative sign. The derivative was negative sign, and then we had a 4 out here and a 4 here, so now it's just gonna be negative 16. All right, good, we're almost there. Let's see, how about, is Fiona here? Fiona, no Fiona?
Yes, sir, hi.
Hey, how's it going?
It's okay, it's doing good.
Okay, how do you feel about giving me the third derivative?
Would it be 32?
Okay, so what are you doing with the negative 16?
Multiplying it by 4.
Okay, so you're gonna have negative 16 here, which comes, right? And then you're taking derivative of this. What's the derivative of that?
Cosine 4x.
4x, and then what pops out the backside of that?
4.
4, okay. And then now we can multiply the 4 times the 16,
okay.
right? And what's that, negative 64?
Yes.
Okay, good. All right, there's our answer.
Okay.
The third derivative of the original function is negative 64, right? Negative 64 cosine of 4x. Now, to answer part B, wouldn't I have to do this again? Like keep going, right?
Mhm.
I'd have
There's a
to keep
pattern,
going.
right?
It has a pattern.
There is a pattern, okay? Maybe let's do another derivative. Let's do another derivative. So what's going to happen here? When we take the derivative of cosine again, now it's going to become negative sine, right? And we know we're going to get a 4 to pop out. And we already have a negative 64 out here, right? So what number will be out in front of this next derivative? This is our fourth derivative.
256.
Positive, right? 256.
Positive 2, yeah, positive 256.
Sine of 4x.
Yeah.
And then when we do it again, the fifth derivative, now we don't get a negative, right? Because the derivative of sine is just cosine.
Right.
1024 negative cosine.
24 and then cosine of 4x.
Yeah.
So wait, hold on.
So you're just multiplying the front number by 4 and alternating a sign and the cosine, kind of.
Yeah, it's kind of alternating a sign, but it's not quite alternating a sign. It's
because it'll be negative next time.
Yeah, this next time it'll be negative. Is everyone clear on that? This next time it'll be negative because when we take derivative of cosine, we're gonna get a negative sign. And then we got to hit it with a 4 again.
It's going by 4s, and is it positive, positive, negative, negative, going
Yeah,
twice?
that's
Okay.
what it looks like. That's what it looks like. So look, we've got, when we do the sixth derivative, let me do this one slower. We have 1024 times negative sine of 4x and then times 4. So the 4 goes out in front. What's that?
4096.
Negative, right? I mean, negative 4096 sine of 4x. That's our sixth derivative. Are y'all following what's happening here?
Yes.
I'm kind of lost. I'm sorry, but I
Okay.
don't know how did we come out with 256?
Okay. So when we are back here at the third derivative, we had to take derivative again, right? So I brought the negative 64 down because it's a constant, took the derivative of cosine, which is negative sine, kept the 4x inside, then took derivative of the 4x, which was 4. Now I have 4, I have a negative, and I have negative 64. The two negatives become positive, and then 4 times 64 gives us 256.
Got it. Thank you.
Makes sense? And then on the next derivative, derivative of sine is cosine, and then a 4 pops out. This time it doesn't change to a negative because derivative of sine is cosine. So we hit that with a 4, we get this. So let me list out what we have here. We have the original function was sine of 4x. When we took the first derivative, we had 4 cosine of 4x. When we took the second derivative, we had negative 16, right? It was negative 16. I'm going to do something a little different though. I'm going to go negative 4 squared sine of 4x. Now the reason I put 4 squared instead of 16 is because you're going to start to see, I'm going to skip a line, so you can start to see a pattern here. The next one, when I take the derivative, we had derivative of sine is cosine, right? It did not change sign, so it's still negative. And we had 4 squared, but we hit it with another 4, so shouldn't this become 4 cubed?
Yeah.
That was the third derivative. That's the negative 64 cosine 4x. The fourth derivative, what happens? Well, I take derivative of cosine, now I get a negative sign. And so it's going to change that negative to a positive. How many 4s will I have now?
4.
4 of them, and now this will be sine of 4x.
Mm-hmm.
And then we go again. So the fifth derivative, let's see, are we going to change to a negative this time or no?
No.
No, it's going to stay positive. How many 4s will I have?
5.
5, and it'll be cosine. On the next derivative, will I change to negative? We're taking derivative
Yes.
cosine, right? So we change to negative. How many 4s?
6.
6.
6 of them, and then this will switch to sine now.
Mhm.
And then let's do another one. The 7th derivative. Okay, am I going to switch signs or not?
No.
No, stay negative. 4, how many 4s?
There's gonna be 7 of them.
7, so 4 to the 7th, and now I've switched to cosine.
4x. Yes.
I have
Alright.
a question.
Yes.
Are we gonna do this all the way to 40?
No.
Okay.
Not necessarily.
Well, we can
We're
already.
doing enough to establish a pattern.
Okay.
Yeah, there's no way, because I mean, I could have made that 400. I mean, the whole idea here is that I want us to be able to establish a pattern. So let's talk about whether or not we get sine or cosine. So do you agree that if we look at the derivatives, if you look at all the odd derivatives, I have cosines, right? And everything that's even, second derivative, fourth derivative, sixth derivative, those all give me sines. Do you agree?
Yes, sir.
Okay. So if we're going to try and find the 40th derivative, well, 40 is an even number, right? So I know that I should have sine or cosine.
You're gonna have sine.
I'm going to have a sine. So I know I have a sine of 4x here. I know that for sure. How about the powers on the 4s? Do y'all see what those are?
It's gonna be to the derivative, so the 40th power.
Yeah, the power is always the derivative number, right? Isn't it?
Mhm.
So we know that we should also have in front here 4 to the 40th power. Agreed? Now the trickiest part of the whole thing is that the signs are not alternating. They're not like plus minus plus minus plus minus plus minus, right? It's plus plus minus minus plus plus minus minus plus plus minus minus. So we now have to figure out where the number 40 is in that sort of sequence of things. Understand? This is the hardest part right here. Do I have any questions though? Huh?
No, I was just wondering, so if we find first 10th of them, like plus, plus, minus, minus, will that continue for the next line?
It should. Yeah, the pattern is that this should continue, right?
Got
We have plus, well, this is a plus, plus, minus, minus, plus, plus, minus, minus. That should continue. I tried to do enough of them that would convince you that it continues. Yeah. Okay, so I'm going to now, I'm gonna write something down. All right. Like I said, this right here is the hardest part. And this is the part that people who have to do more like computer science, pretty much everyone in this class that needs like engineering, computer science, this is something that you don't really get a lot of formal, like, you're not like formally introduced to this. And so when you first see it, you're like, what? Okay, so just see if you can follow me. Do you agree with this? If the derivative power, or the derivative, right, is, let's say, 1 or 2. Let's see, so that's, sorry, not that. Let me do it this way. If the derivative is 1, first derivative, if it's the 4th or 5th, or let me see, what would be next? I'm trying to figure out when they're positive. Maybe I should write it this way. The derivative is positive if we're looking at the first derivative, fourth derivative, fifth derivative, right? That's the first derivative, the fourth, the fifth. Which would be the next ones?
The 8th and 9th.
The 8th and 9th. What would be the ones after that?
12th, 13th.
12, 13. So how are you figuring that? You're correct, but try and help explain this to everyone, how you're thinking through that.
Oh, you're just skipping the next two numbers.
You're just skipping the next two, right? So you go 12, 13, you skip 14 and 15, so the next two would be
16 and 17.
16, 17, right?
You just add 4 to the number.
What's that?
You just add 4.
Mm-hmm. Yeah. So looking at, let's figure out when is the derivative negative. If we're looking at what, 2 or 3, what else? Second or third derivative, or the 6th and 7th?
7.
Okay, right.
10, 11.
So you skip again, 10, 11, right?
14, 15.
Yep. Do you all understand what we're doing here? We're just making a list of when it's positive, when it's negative, right? And what you need to figure out is which of these lists is 40 in? Is 40 in this list or is 40 in this list? Right? If 40 is in this list of numbers, then our derivative is positive. If 40 is in this list of numbers, it's negative. Are y'all with me?
Yes.
Okay. Now, the way that I'm going to do this is not what you think you want to do. First, I'm just going to ignore all the odds. Okay. I'm going to ignore all the odds. I'm ignoring odds because my number is 40, right? I'm looking at 40. So I'm just going to ignore the odds. I'm going to ignore the odds here. Now, look at the numbers that we have left, right? They're even. 4, 8, 12, 16, compared to these 2, 6, 10, 14. And again, the question is, where does 40 live, right? Where does the number 40 live? Oh. Sorry, I heard. Never mind. Okay, so where does 40 live? So I'm about to show you something called modular arithmetic, and a lot of you have never seen this before. So here's what it is. You have to look at how much these are jumping by. So how much do those numbers jump by each time?
4.
Going by 4.
4, right? How much do these jump by?
4.
4. 4. So modular arithmetic works this way. You take, if I take this number, let's take this number 4 right here. I'm going to write this down. I'm going to tell you what it means. 4 mod 4. So this number 4 is how much we jump by each time. I'm taking that number 4 and I'm asking you to do this. When I write 4 mod 4, I'm asking you to do this. Take this number 4 and divide it by 4. Okay, everyone take the number 4 and divide it by 4 and tell me how much your remainder is.
1.
1.
Well, 4 goes into 4 one time. I'm saying if you take the number 4 and divide it by 4, it goes in once, 4 goes here, you subtract, you get a remainder of what?
0.
0. Okay, now I'd like you to take the next number in the list, which is 8. I'd like for you to do 8 mod 4. So that means take 8 and divide it by 4. Tell me how much you have left. What do you have?
0.
0 again. Understand?
Yeah.
Take the next number, 12. 12 mod 4. What's 12 mod 4?
0.
0 again. All of these numbers in this list, when you do mod 4 on them, you get 0. Do y'all see that?
Yes.
Okay, try it on the other list. 2 mod 4. Let's skip 2 mod 4. Let's do 6 mod 4 because 2 mod 4 is probably going to confuse you. What's 6 mod 4? So what happens if you take 6 and divide it by 4? You're going to go in there one time, 4, subtract 4, you get 2. Isn't your remainder 2?
Yes.
Okay. Take the next number in your list, 10. What's 10 mod 4? So how many times does 4 go into 10?
2.
2 times. How much is left over?
2.
2. You'll see that?
Yeah.
If I do the next number, 14 mod 4. So 4 goes into 14 3 times, right? 3 times 4 is 12, and you have 2 left over. So do y'all see that every number all the blue numbers here, right? All those blue numbers, when you do mod 4 on them, you get 2 as an answer. But everything that's in yellow, when you do mod 4 on them, you get 0. That's what distinguishes these two lists from one another. So the question is, what's 40 mod 4?
The top one.
Is it? If you do 40 mod 4, that means how many times does 4 go into 40? Well, it goes in there 10 times evenly, right? Without any remainder. So that means that you must be in that top list, which means our answer must be positive.
So is it gonna be always mod 4 or
No.
the mod will change?
It doesn't always have to be mod 4. It depends on the pattern. See, we had to recognize the pattern that it went from 4 to 8, then to 12, then to 16, right? So that it jumped by 4 each time on both of these. If it jumped by 3 each time, then we'd be doing mod 3. Okay. So to come back to our final answer, we were trying to figure out, was this plus or minus right in front? We know it's a plus. And we know it's plus because we know that 40 mod 4 is 0. So now if I asked you, I could say now, hey everyone, let's find the 1342nd derivative of this, right? If I asked for this, then you would do this mod 4, right? 1342 mod 4. So you could probably do that on your calculator. 1342 divided by 4. You have a remainder there. So this would, we know that the answer to this would be negative. And then it would be 4 raised to that power. And then would it be sine or cosine? Because it's an even number.
Sine.
Yeah, it was, all the evens were sine, so sine 4x. Okay, I'm going beyond where I want to go. I just want you to, I wanted you to see that there's a way of doing this, okay? There's a way of doing this. I would probably only offer this as a bonus question, all right, on a test. I might ask you for the first 3 or 4 derivatives, but I'm not going to ask you for the 40th derivative. All right. For those of you who take Cal 2, this will come back. You'll see this again, this stuff.
Oh, you mean the mod 4 or like just
The modular arithmetic.
Oh, okay. Yeah, I'm ready. Let's do it.
All right.
Hey, Professor, just a quick
Yes.
question. When we did that problem like part A,
Mhm.
right? When it was, when there was a derivative second derivative, and we took a third derivative. So why did we come out with why didn't we do a layers? Why did we just like took 16 out and then took a derivative of inside?
Why did we not mess with the 16?
No. So like, I remember we did one time like 16 out and then put everything in a parentheses and take a derivative of inside and then do it again. I don't know. I'm just like looking at it as a 3 layers of it.
Okay, it's because, first of all, this is a constant, right? Attached to a function. Anytime you want to take the derivative of a constant attached to a function, the constant just comes for the ride. It always just comes for the ride. If the constant is out front, you can just bring it down. Then this is composition. That is 4x inside of sine, right? Hush. Kick those dogs. I'm kidding. I wouldn't kick my dogs. Jeez. Am I making sense or not in terms of the constant coming for the ride?
Yes. So you meant like any sort of number, it just always comes out, right?
If as long as it's attached to a function of x.
Right.
If it's by itself, we know derivative of a constant is 0. If it's by itself. but if it's attached to a function, then it's going to just come for the ride. All right. Okay, chain rule. Trying to see if there's anything else I want to do here. How about I give you a few problems? Because I'm ready to move to the next section, but you will be dead in the water in the next section if you don't understand chain rule. Okay, so let's just do a couple of problems to make sure we're warmed up before we try and jump into this next thing. All right, so here are some problems to do. Oh, no, sorry. Okay, let's just do those 4 problems right there. I'm going to give y'all like 10 minutes. Let's see, do y'all want to do breakout rooms? Do y'all care?
Sure.
I'll do breakout rooms. You can join if you want. If you want to work on your own, you don't have to. But try not to be just chit chat. Try and get work done. All right.
Sir, could you go back to the problems? I didn't get the 4th one down. I'm sorry.
Give me just a second.
Yes, sir. Okay, I'm good. Thank you.
Okay, I think everyone's back. I have put the solutions up here so that you can check to see that you were doing them correctly. And let me just double check them all real quick because I went real fast through that. Okay, yeah, that looks good. I did have a question about when the next test is, and I'm thinking April 6th. I'm thinking 2 more weeks, and then we have the test. Maybe we push it into the end of the month. Maybe we do it on the 31st, or sorry, on the 1st. Yeah, I think the soonest it would be on April Fool's Day. Is that right? Would that be April Fool's Day? That'd be the soonest. We might push it to the 6th. We'll see. Let's see how things go in the next. Let's see how next week goes.
Sir, I got them all right. I just had a question. Do we have to turn the when we have a negative 1/2 with the 1/2, do we have to turn it into the fraction form, or can we leave it as the
You can leave it the other way.
Okay.
Yeah. I think though, for your own sake, moving ahead as we have to start to simplify these things, that it would be easier to work with it in its square root form as opposed to the negative exponent, just for what we're going to do later. Okay, hopefully you did okay on that. I'm not going to go over these. I'm just going to move on. We need to start the next section. So if we kind of take a step back now and just kind of talk about what we have achieved in this class, it's basically that if somebody were to hand us a function, right? Some y equals f of x. We now have equipped ourselves with these rules, power rule, product rule, quotient rule, chain rule, that we should be able to go to any point on the graph and then find the slope of the tangent line on that graph. And to do that, to find that slope, all we have to do is take the derivative of the function and then plug in whatever that x value is into that derivative, and we will have the slope of the tangent line. Right? That's what this has all been about. And what we can actually take the derivative of now is really, we've blown the doors open. We can take very complicated functions and still be able to come up with a meaningful formula for the slope of the tangent line. So that's what all of these represent, right? But we're still limited in the sense that to do this, we must be looking at a function of x. Meaning that whatever we're looking at, it must pass the vertical line test. So it must be a function. If we have something that is not a function, we do not have a way of finding the slope of the tangent line. And that's what the next section is about. So we are now going to be interested in this thing called implicit differentiation. So this first part is me just explaining what I just explained. So far, we can handle it if we have y is equal to a function of x, which means that as long as we can isolate the y in the equation, as long as we can get y equals something with x in it, like all these problems I just gave you, y equals this, y equals this, y equals this, y equals this. As long as y is isolated, we have all the rules to help us, right? But sometimes we can have an equation where we cannot solve for y. And we might still be interested in knowing what the slope of the tangent line is. So we have to distinguish between what are called explicit equations and implicit equations. These are all explicit, meaning I can solve for y. See, y is now on the left side and x is here. Here, y is solved for and I have x's here. So the y's and the x's are separated and we have y by itself. Also, if you can get x by itself and have nothing but y's on the other side, that is also an explicit equation. As long as you can solve for one of the variables, then you're looking at an explicit equation. Implicit equations are equations where you cannot solve for y or x. So look at this first example here. If I were to take this and say solve it for y, what you would do is you would take the x squared to the other side by subtracting it. And then if you tried to solve for y, you'd have to take the square root on the left side, and you'd have to take the square root on the right side. And as soon as you come in and take the square root on both sides, you would have to do plus or minus. So the left side would become y, but the right side would actually become two different things. And so you don't now have that y is a function of x. You have that y is actually two different functions. It's the square root of 16 minus x squared, and it's also negative square root of 16 minus x squared. And so these two are completely different functions. They're not the same. Do you understand what I'm saying?
Yes.
Okay, so when you cannot solve easily for y, you're looking at an implicit equation. This next one, I'm not going to go through the algebra, but nobody in here is going to be able to solve for y. There's just no way it's happening. And this is another example. There's no way you're solving for y. You'll never get y by itself, and x is on the other side. But all of these equations have graphs. Okay, all of them do. I'm going to show them to you. Okay, I'm going to show you the graphs of all of those equations right now. Maybe. Bring up my graphing software here. So let me show you that first one. The first one was x squared plus y squared equals 16. Well, that should look familiar to you, right? That's a circle, and it has a radius of 4. And so, I mean, we should be able to at least ask the question, hey, if you go to this point, what's the slope of the tangent line, right? I mean, we should, as calculus students, as human beings, right, as the human race, we should be able to figure out the slope of that line, even though it's not a function, right? It fails the vertical line test. We should still be able to do it somehow, some way. The other one, see, this one was weird. X cubed plus cosine of y equals, this is going to be a cool graph, x plus y squared. There we go. See this thing in blue? That is a curve in two-dimensional space, right? It's not a function of x. It fails the vertical line test. But again, we should, if our math is good at all, right? If it's worth anything, we should be able to pick some arbitrary point and find the slope of the tangent line. Let's look at the next one. This is my last one. Cosine of x times y equals 1 minus sine y. What the hell is that?
It's art.
A green grass.
It's crazy, right? Isn't that a crazy function or crazy? It's a crazy equation, right? And that's nuts. So, but we should still be able to go to some point here, right? We should be able to go to some point, just pick a point, I don't know, and find the slope of the tangent line. We should. How though, right? How? All right, so that's what this is about. How do we do this? Seems exciting, right?
I've never thought math could be that fun.
Well, you know, here's the thing you really have to think about. In the real world, right? In the real world, if our calculus is only good at dealing with functions, right, that pass the vertical line test, how many things in the real world, just think about an object moving on a surface. How many times do we actually have the control to make sure that that object moves so that it will pass a vertical line test? Just think about, like, if you just take an ant and just put the ant on the ground and let it walk around, right? If you wanted to figure out like its velocity at any point or something, then if that ant decides to, you know, walk and then make a turn and go like that, you can't have your math fall apart, right? You still have to be able to deal with that because now you don't have a function anymore, right? So in the real world, we need to be able to deal with objects that move and don't behave like functions. Does that make sense? So it's applicable to the real world because the real world doesn't always work the way we want it to work. All right, so how are we going to do this? Well, we have to introduce this new concept called implicit differentiation. Okay, so we now study a new form of differentiation, and it's called implicit differentiation. And the only way to explain it to you is to do examples. All right, so that's how we're going to do this. There's not a formula. Okay, there's not a formula. There's just an idea. All right, so here it is.
Is this where we use Leibniz notation?
Yeah, we're going to switch to Leibniz now. Exactly. Okay. So up to this point, when I've given you y equals a function of x, I've been asking you to do this, find f prime, right? And you've been like, oh, I just find the derivative, right? Or I've been saying find y prime, and you've been saying, oh, I just go take the derivative, right? That's what that notation is meant. But there was another notation by the other father of calculus called Leibniz notation that would have looked like this, dy dx. And we haven't used that much. The book did use it in the homework a little bit, but we have stayed away from this. And now I'm going to start using it. So everyone needs to understand now that when I write dy dx, what I mean is take the derivative of this function, right? Yes? Okay.
Does dy dx mean to take the derivative in respect to x?
Yeah, but I haven't talked about what that means yet. I'm
Okay.
about to. I'm about to do that. I'm about to do that.
I'll just
so let's take a look at this example right here. Sine x to the third power. Okay. When I've said to take the derivative of this in the past, I would have said find y prime, right? Find y prime. That's what I would have said. I'm going to do it a little different now. What I'm going to do now is I'm going to say find dy dx. Okay, dy dx. So when I write that down, here's what you're going to do. Here's the new way of looking at things. You're going to take this equation and you are going to differentiate both sides of the equation. And you're going to do it with respect to x. And what I mean by that is this. We are going to take the left side of the equation. We want to know what the derivative of the left side of the equation is with respect to x. By me putting dx on the bottom, that means I want you to treat x as if it's the independent variable. It's the thing that's getting plugged in. Okay, x is getting plugged in and y is what comes out. I want you to do that on the left side. And on the right side, I want you to take the derivative with respect to x of this. So it's a new notation. That's all it is, but we're going to be doing the exact same thing. So let's start with the left side. If I take the derivative with respect to x of y, then just imagine that y just goes up here next to the d and becomes dy dx. And that means y prime, right? That really means y prime. Then the other side of the equation, I'm going to just take the derivative with respect to x of this the way that we've been doing it. I mean, there's nothing new here. So we bring the 3 down. Okay. We rewrite the sine x, this is chain rule, to the second power, right? And then you say times the derivative of the inner function, which is cosine of x. And so this is our answer. Do y'all see I've done nothing new? It's just a notation thing here. Specifically me writing this in the beginning instead of writing, just going and getting the derivative. I'll do another one. It's my time. Okay. So let's say we have y equals, I'll make this one real easy. And I say find dy dx. Okay, so what we do is we start on the left-hand side. We write, okay, I want the derivative with respect to x of y. And then I want the derivative with respect to x of x squared plus x plus 1. All right, what is the derivative with respect to x of y? What does that become?
Y prime.
Y prime, or I'm going to write dy dx, okay, instead of y prime. But that's what that means, right? Again, it's almost like the y just pops up here. It becomes dy dx, and that's what we're looking for in the problem, right? We're looking for the dy dx, which really means y prime. On the right-hand side, I want to take derivative with respect to x of these three things. And since, you know, there's addition, we can just do them individually. So we get 2x plus 1, and we're done. Again, nothing different, right? Nothing is different so far. Just the notation. All right, so now I think it's time to turn the screws a little bit, all right? So pay attention, because this is where things get weird. Let's try this equation. That was the problem I showed you earlier with the circle, wasn't it? That's the circle. Here's what I want you to find. I want you to find dy dx. Now, it is not solved for y, is it? This is not solved for y. But we're going to do the exact same thing we just did. I'm going to take the derivative. I'm going to take the derivative with respect to x on the left side of the equation. And I'm going to take the derivative with respect to x on the right side of the equation. So it's like we're doing the same operation to both sides. Now let's start with the right side, because the right side's easier. What is the derivative of any constant by itself?
0.
0. Okay, so the right side's 0. We're happy about that. Now, on the left-hand side, y'all see we have addition here. So we can do these separately. So my next step is really, I'm going to take the derivative with respect to x of x squared, and then I'm going to add to that the derivative with respect to x of y squared. Okay, here it is. Here's the part. Here's the part that the wheels start coming off for people, all right? What is the derivative with respect to x of x squared?
2x.
What do you think it is? What?
2x.
2x, right? Okay, that makes sense. 2x, that's what it's been this whole time. And that is correct. This is just 2x. All right, plus. Now, right here, this part right here is the part that people mess up. What we're doing here is we're saying, take the derivative with respect to x of y squared. So notice that the variable here is y, but the variable here is x. Those are different variables, aren't they? So I want you to just separate yourself from this over here. And I want you to look at this as I'm asking you to take the derivative with respect to x of something squared, right? Of something squared. Now, in this case, it's y squared, but it's something squared. What is the derivative using chain rule? What is the derivative of something that's being squared?
2 blank.
2 times that something, right? To the first power. Agreed?
Yeah.
Then continue the chain rule. Now you have to take what? The derivative of what's in here, don't you? The derivative of that box?
Yes.
Okay, so I have to still take the derivative with respect to x of the box itself. So the 2 had to come out. Then I rewrote the box to the first power. Then I said times the derivative of what's in here, which is this. Let's try and do that back over here. What is the derivative with respect to x of y squared? So the box here for us is the y. So bring the 2 out first. What do you get? 2y to the first power, right? I don't need to write the 1. But then this is the critical part, times, now I need the derivative with respect to x of what?
Y.
Of y. Do you all see that? because we did not have to do that over here because these variables were the same. So the derivative of x squared is just 2x. But if the variables aren't the same, then you have to run through the chain rule. 2 comes out, y to the first power, then times derivative of the blue part, which is the derivative with respect to x of y. And that must be equal to 0. I'm not done, okay? Any questions right now at this point? We're gonna do more examples, but any questions up to this point?
Is it finished?
Nope, not done. Because remember, what did we want? We wanted dy dx, didn't we? That's what I wanted you to find. So right now, here's what we have. 2x plus 2y. And remember, this in yellow here, be careful there. That's a 1. That's not a prime, right? That's not like a prime mark. That's a 1. So I have 2y. And then what is this? What is the derivative with respect to x of y? Isn't that just dy dx?
Yeah.
That's what it is, right? You just, again, slide that little y up top with the d, and that must equal 0. And we are now supposed to solve for dy dx, right? That's what we wanted. So just start moving things around. Let's isolate this. So I will subtract 2x on both sides. And then to get dy by itself, dy dx by itself, I'm going to divide both sides by 2y. And that means dy dx must be, let's see, the 2's can go away. I get negative x over y. All right. What did we just do? Let's see. Let's go back to this. Here was that circle, right? We just figured out that if you want to know dy dx for this circle, it's going to be, what was it? Negative x over y. All right. So let me go to a point. I'm going to go to a point on this circle right here, okay? And you know what? Yeah, let's just keep it this way. If I want to know the slope of the tangent line, then all you need to do is tell me what that point is. If you tell me what that point is, whatever the x coordinate and whatever the y coordinate is, I will plug that into this formula and that will give you the slope of the tangent line. Now, I don't know the points on this circle, so it's going to be hard for me. I can pick one here. You know, I can go and pick a point. And what this is saying is you take the x coordinate divided by the y and make it negative, and that's the slope. What's cool about this is, what's cool about this is this. I can do this for a couple of points and prove to you we got it right. If I take this point right here, can somebody tell me what that point is? Like what is the ordered pair there?
0, 4.
0, 4, right? So let's plug that into this. What would happen if we plug 0 into the top and we plug 4 into the bottom? What would we get?
0.
We'll get
0. And do you agree that the tangent line up here would have a slope of 0 because it's flat? Right? That's what this calculation just told us. It would also work down here at this point, 0, negative 4, because if we plug in 0 for x on top and negative 4 on the bottom, again we get 0. So that would give us a slope of a tangent line here of 0. What I think is really cool is what happens here at this point. What's this ordered pair?
Wouldn't it be undefined?
4.
It'd be 4, 0. That's the ordered pair, right? So now try and plug that into this formula. It'd be negative 4 over 0. Uh-oh. Division by 0.
That means there's a hole there?
No, it means the slope of the tangent line is undefined, right? That's what it means. The slope of the tangent line is undefined. So if your tangent line has a slope of 0, it's flat. But what's the slope of a vertical line?
There is no
You
slope.
don't have one.
It's undefined, right? It's undefined. And that's why at this point, we know that the tangent line is vertical, don't we? And our formula is actually telling us that, right? Like at that point, 4, 0, we try plugging into this formula and we have a problem, which tells us that our tangent line is vertical. I hope that makes sense. There's one more thing I could maybe convince you of, is that if you were to go to 45 degrees here, do y'all agree at 45 degrees, whatever the x coordinate is, the y coordinate's the same thing?
Yes.
Right? So if these are the same numbers, then if you plug that into this formula, if these two numbers are the same, then what would your answer be?
1.
-1.
Yeah.
Right? -1. And would you agree that the slope of the tangent line there would be -1? Yeah. So we have a way of doing this, all right? I don't think I have enough time to get to the next example. I want you to make sure that you've done all the chain rule homework. Get yourself caught up this weekend, even if that means you go back and do product rule, quotient rule homework, redo it. Whatever it takes, spend this weekend getting yourself completely comfortable with all of the differentiation rules, all right? We're not going to start any homework for this section. What section is that?
2-6.
Yeah, we're not going to be doing, I'm not going to assign you anything out of this homework, this section 2-6. I'm really just wanting you to make sure that you've got all 2-3, 2-4, 2-5 down. And then once we get to 2-6, it's going to get real. And 2-7 is, there are 2 sections in this class, 2 topics that are the hardest in the class. 2-7, okay, because it's word problems. And then optimization problems, 4 or 5, which are again word problems. So since I have 1 minute, I'll show you, you know, like I think you have a feel for where you are right now in terms of what we've seen. Like you have an idea of the types of problems that we've been doing. Let me show you an example of a problem from the related rates section. Okay, just so you can get a feel for like what in the world we're about to do. Okay, here's a good one. Here's a problem. A plane is flying horizontally at an altitude of 2 miles. Okay, so you got a plane that's 2 miles high, flying horizontally, and that plane is flying at 600 miles an hour. The plane is headed directly over a ground-based radar station. So on the ground, there's a radar station, plane's flying overhead. At the moment the plane is 6 miles from the radar station, how fast is the distance between them changing? So that question is asking, as the plane flies over, if you had a rope connecting you to the plane, how fast is the rope coming out of your hand? Right, that's a related rate problem. There's a lot of geometry involved in this. I have pictures that are going to help us see what's going on. Another problem. Here's one.
The cone.
Yeah, the cone one's a good one, but this one is this blue line represents a street light, and this is a person, and the person is walking away from the street light. And if the light's on, then the light is casting a shadow. And so the person's shadow is on the ground. Let me pause this. And so this person is walking. This is a person. There's their body and legs. And then on the ground is their shadow. And as the person walks, their shadow is growing. And so what we're going to ask is at a specific instant in time, how fast is the tip of the shadow moving? Now, these problems just get crazier and crazier. This one is one where you have a cup and you're filling it with liquid and everything's happening real time. And then we just say, hey, at that moment right there, how fast was the water level coming up?
Will we use limits in it?
We're going to be using implicit differentiation.
Oh yeah.
Okay, so the reason I'm showing this is because next week we start implicit differentiation, which leads us directly into related rates, one of the hardest sections in the class. You can't do implicit differentiation unless you know chain rule, product rule, quotient rule, power rule. You have to know those. So I really want you to invest time this weekend so that you come in here and next week we're not sitting here and I'm still trying to explain to you what a product rule is. All right, because at that point, the train has left the station. All right, so take advantage of that time, and if you put in the time and the effort, it'll pay off, I promise. Okay, have a great weekend, everyone.
Bye,
Thank you,
guys.
sir. You too.
And again,